If you recall, the difference of squares form looks like the following. Okay, so if you are asked to factor and the expression has two terms and each of those terms is a perfect square separated by a negative sign, then it has a special factor form. And that special factor form is it's just going to be the sum and difference of those two bases being squared. So if you have an a squared minus a b squared, you take the two terms, a and b, and it factors into the sum and difference of those terms. Okay, so again, if we take a look at some examples of this or what this looks like. From the most basic form, it looks something like this. You have difference of two squares here. Okay, so it's the base of x squared minus the base of 3 squared. If you look at that and identify what those bases are that are being squared, so x and 3 are your two bases being squared, and it just factors into the sum and difference of those bases. Okay. Now, you're going to start to see some, so we've already done that, so hopefully that looks familiar to you. All right, what you're going to start to see on these is some that get a little more complicated within or with respect to this same pattern. Okay, so if you saw something that looked like this, oops. Okay, and you were asked to factor this expression. Okay, the way that you would approach this problem is you could do it one of a couple ways. One, if you look and identify, do you have two perfect squares that are being subtracted from each other? What base can you square to get 4x to the fourth? You square what to get a 4? 2. Square what to get x to the fourth? X squared. And then what do you square to get 16? 4. So when you look at this, you wind up with the same pattern. We have the difference of squares, so it factors into the sum and difference of these bases. So 2x squared and 4 are the bases. Okay? And oops, let me go back. I didn't want to put the 4 there to start with, so hang on just a second. All right, so let's just take this expression here. So x to the fourth minus 16. When you're looking to see, does this fit the pattern? You want to find out, are there perfect square, or are there bases taken, or that you can square to get each of these expressions? So what base do you square to get x to the fourth? Here it's just an x squared, and to get 16 was the 4. And so when you're looking at this, it does factor into that pattern of the sum and difference of the terms being x squared and 4. So if you take those two terms, you take the sum and the difference of those, you can look to, you factor them. And now, you're not done yet. And the one thing, when you start to work with higher degree polynomials, you still have to kind of cycle back through and look to factor everything completely. So when we look back at this problem, the x squared plus 4 can't be factored any further. So we leave that as it is. But the x squared minus 4, the difference of squares, fits this same pattern once again. So it factors into the sum and difference of the terms that are being squared. Okay, so the base that you square to get x squared was x. The base you square to get a 4 is 2. So it factors into the sum and difference of those. And so that winds up giving you your overall factored form for that expression. All right, now this comes up or brings up another issue, this x squared plus 4. Why doesn't that factor at all? Okay, that's called the sum of squares. Okay, the sum of squares is said to be irreducible over the real number system. Okay, we may come across the times where you're asked to find all roots, including the imaginary ones, but in the real number system, the sum of squares can't be factored any further. So be aware of that. It's not gonna, it will stay that binomial. There's nothing you can do other than potentially remove a common factor from it. Hey, the other factoring rules that we went through were those of a perfect square trinomial. Okay, for most of you, this isn't necessarily a quicker pattern to use, but I'll write it down anyway. Okay, there's two forms of this. The form where you have a negative sign in between, or for your second term, and the form where you have a positive, a plus. Okay, and each of these, the perfect square trinomial form just allows you to factor it into a binomial square factor. Okay, so if you have the same two binomial factors, it's a binomial square. The expanded version, the polynomial form of it, is a perfect square trinomial. And what you do is you just take the term that you square to get your first and your last term, and then it's whatever sign is in the middle. So here it's a plus because this is adding the middle term. When you subtract the middle term, it's a negative. Okay, so again, these are something that we already looked at a little bit. You can reverse FOIL to get the same answer. You can also use your calculators for those. But I do expect that you can do difference of squares by hand pretty easily. All right, let's take a look at the factoring rules we're going to add to this. Okay, so there's some additional factoring rules that we're going to add, starting with the sum of cubes. Okay, so the sum of cubes has the following form. If you have two terms that are both perfect cubes, they're added together. Okay, they do have a special factor form. Okay, the special factor form, there's two factors. The first factor is a binomial, the second factor is a trinomial. Okay, and the binomial factor is just going to be the sum of the bases that are being cubed. So A and B added together are going to be your first binomial term, or your first binomial factor. And now your second factor is a trinomial, meaning it has three terms. The first term is the base that's our first term squared, so A squared. The last term is our second base squared, so B squared. And then the middle term is just the opposite of the products of these bases. So A times B, change the sign, gives you negative AB. And so that gives you your special factor form for the sum of cubes. Okay. Let me go ahead and show an example of that. All right, so if I gave you the following. And I ask you to factor this. Okay? It needs to, in order for this to be factored, the first and last terms need to both be perfect cubes. So let's kind of take a look and see what our list of perfect cubes would be. So 1 cubed is what? 1. What's 2 cubed? 8. 3 cubed? 27. 4 cubed? 5 cubed? 6 cubed. And then the only other one that I would expect you to know would be 10 cubed, which is 1,000. Those are the ones that I expect you to know without a calculator. You can use your notes, so if you have this list in your notes, that's helpful. Okay, but if you need to be able to recognize these numbers as being values that can be expressed as a perfect cube. Okay, so when you look at this, and you have 64x cubed, is there a base that you can cube to give you 64x cubed? Well, here's 64, so we cube what base? 4, and then we also cube the x. So here's our first base that we're cubing, and then what number do you cube to get a 1? Look right here, a 1. So this fits the pattern of the sum of cubes. So when you factor this, it's going to be two factors, a binomial and a trinomial. The binomial is just going to be the sum of these bases, so 4x and a plus 1. And then to find the trinomial factor, you take this first base and square it. So you square the 4, square the x. The last term of that trinomial factor is the second base squared. So if you square the 1, you get plus 1. And then the middle term right here is just going to be the product of these two bases with the opposite sign. So 4x times 1 is 4x, change the sign, negative 4x, and you get your factored form. Now, even though we're dealing with the sum of cubes, this same rule holds true for the difference of cubes. Okay, so if you were looking to simplify the following, or to factor the following, okay, the same thing holds true. Whether this is a sum or a difference, these same rules will apply. So if you're looking at this, you have a base of what can be cubed to give you 27x cubed. 27 gives you a base of 3, and then x can be cubed. And then for the second term, what number can you cube to get a negative 8? Not just a 2, but a negative 2. Use the sign. If you allow the sign to kind of carry with it, the signs will all take care of themselves in the factored form. So here, this does fit the pattern that we're looking at. It is the sum of cubes here. So it's going to have a binomial and a trinomial as your factors. The binomial is just the sum of these two terms, 3x and a minus 2. So 3x plus negative 2 is just that expression, 3x minus 2. It's still, I'm just showing that it still fits this pattern. It's one perfect cube plus another perfect cube. Okay. So now when you look at your second factor, the trinomial, you're going to take this first base and square it. So what's 3x squared? Square the 3, square the x. Our last term of the trinomial is going to be our second base squared. So if we take negative 2 and square it, what do we get? Plus 4, right? Negative 2 times negative 2 is a positive number. And then to find our middle term, we take the product of these bases and we change the sign. So 3x times a negative 2, negative 6x, change that sign, positive 6x, and that takes care of the signs. Okay. Now, you could think of these as two different patterns if you want, okay? Because this really is just the difference of cubes. So if you wanted to think of the difference of cubes as its own pattern, you could. A cubed minus b cubed. It is going to have a binomial and trinomial factor. Okay? And here, if you just take the difference of these bases, a minus b, and then this trinomial factor is the first base squared, the last term is the second base squared, becomes a plus b squared, and then the middle term is just the opposite of these, the product of these. So a times a negative b is negative ab, change the sign, plus ab. The same rules hold true. I mean, you can see you can use it either way. I just prefer to work with one rule rather than two different rules. All right, so try this problem here on your own and kind of compare, see what you got compared to somebody sitting near you. All right, so see if you can completely factor this expression first. All right, if we look at this, are these the difference of two cubes? No. Is there any way that you can transform them so they are? Anytime you're looking to factor anything, and we'll talk about the steps here in just a moment, but if you recall, the first step in factoring is always to look to remove any common factors. Are there any common factors between these two terms? Yeah, take out the 3. When you do, you're left with an x cubed minus 8. Now do you have perfect cubes? A 1 and an 8, so they are. And so you can look to factor them. Okay. When you look to factor these, the 3 stays as it is. You do have the difference of cubes, so it factors into this pattern up here. If you think of the bases that are being cubed, you have an x and a negative 2. So we take the sum of those bases as our first binomial factor, x plus a negative 2. And then our second factor is a trinomial. You're going to take our first base, the x, and square it. The last term of our trinomial is the second base squared, so negative 2 squared is plus 4. And then if you take the product of those bases and change the sign, it's your middle term. X times a negative 2 is negative 2x, change the sign, and that gives you your final factored form.